We're going to wrap up gas laws by talking about two properties of gases, what happens when gases mix and what happens when gases move across concentration gradients. So we're going to start with our good friend John Dalton, who you'll remember John Dalton gave us the modern atomic theory. There were 4 parts to Dalton's atomic theory, and in large part, Dalton came upon his atomic theory by considering things like intermolecular forces. Um, he had a general concern over whether or not atmospheric humidity, water vapor in the air, was a chemical or a physical process, how the mixture of gases in the air worked. And while investigating these ideas and the ideas of some of his contemporaries, he came up with what is now known as Dalton's law of partial pressures. And essentially, what he sorted out is that a gas will expand to fill a container. And it will expand exactly the same way, whether it's the only gas in the container or whether it's mixed with other gases in the container. So we think about that center picture, gas B, those yellow particles there. They're gonna disperse and spread out from themselves exactly the same way if they are the only gas or if they're mixed with other gases. And so what he was able to sort out then is that all you're really doing when you add gas particles to a mixture is you're increasing the collision rate. It doesn't really matter what kind of particles are colliding with the walls. They're all relative to the size of the container, roughly the same size. And so each of these gases in the top of this picture carries a pressure relative to the number of collisions they have with the wall. Dalton, of course, didn't talk about it in terms of particle collisions, but it's essentially the same concept. And then when you mix all those gases together, you're essentially adding the total number of particle collisions over a given period of time. And so each of those gases will carry what's called a partial pressure. And so the total pressure in the container is just going to be the pressure of collisions by particle A plus the pressure of collisions by particles B particles and pressure of particles of collisions created by C particles. And so there's just this additive feature. And with respect to the atmosphere, right, we can talk about the different gases that are mixing in the atmosphere. And we know that nitrogen has the highest concentration. It makes up just short of 80% of the atmosphere. Oxygen is about 20%. And then you have, of course, a bunch of variation of water depending on where you are in the world. Some air is drier than others. Argon is the next most abundant, and then some CO2. And then we could keep going because there are other gases in the atmosphere. Of course, there are various pollutants because of industrialization. During volcanic eruptions, this is going to change, but this is kind of your average most abundant substances in the atmosphere, and all of those things are going to add up. Their individual pressures are going to add up to that total pressure of the atmosphere, 101.3 kilopascals, or 1 atmosphere. And of course, that measure across the bottom is pounds per square inch. So that's how Dalton's law of partial pressure works. Second topic we want to look at is the movement of gases. And there are 2 concepts we want to look at. We want to look at the idea of diffusion and effusion. And both of these things work by moving across concentration gradients. It is matter moving from areas of high concentration to low concentration. And diffusion is just that spreading out of that process. And so here at the top left picture, we have this particles that are in this container. They're going to spread out to fill the container. These might be gas particles in otherwise a vacuum. These might be solute particles in a mixture or in a solution, but they're going to eventually spread out. The difference between diffusion and effusion is just effusion is the same movement, but through a tiny opening and a barrier. And so the barrier has to be a certain percentage of the size of the molecule for it to be considered effusion. So if you look at that picture right next to effusion, once that hole gets to be bigger significantly bigger than the size of the particle, then we're still just talking about diffusion, the kind of free movement of particles in space as opposed to a restricted movement. Effusion is why a latex balloon that you blow up over time loses pressure. It loses gas particles because latex actually has is microporous, and roughly those holes are roughly the same size as molecules in air. And so all of these are talking about, or both of these, I should say, are talking about moving across concentration gradients. You may remember a similar process from biology where particles move across a variable um, membrane, where only certain size particles can cross through that membrane. And so particles move across the concentration gradient in a semi-permeable membrane. That, of course, hopefully you were thinking in your head, is called osmosis, right? So we have these three different concepts. They do not all just refer to gases, but we're going to excuse me, we're going to consider just gases as we talk about this next bit. And we're going to look at what's called Graham's Law of Effusion, or sometimes Graham's Law of Diffusion. It works both ways, in that the ratio of the rate of two different particles. So you can think about dinner being cooked and dessert is in the oven. And so we've got something baking in the oven, we've got something cooking on the stove, and the scent molecules that come off of those two different things being cooked are going to move at different speeds. And so you may smell the cake before you smell the cooking dinner, or you might smell the sauteed onions before you smell the cookies baking, just because those particles are going to be moving at different speeds. And the ratio is the inverse of the square root of their molar masses. Essentially, the idea here is lighter particles diffuse or effuse faster than heavier particles. And so this is a simple statement of ratios that you can set up where we look at the movement of gases, either free movement or restricted movement, as is the case with effusion. And all of these things are just thinking about the speed of particles because of their temperatures, how much space they have to move around in, what are the pressures being exerted on these particles. And all of those things, again, boil down to the kinetic theory of matter, which says we have this list of properties that we are interested in measuring that describe the state of a gas. And they can all be described in terms of reference to their individual particles, in terms of motion and collisions. And yet the actual individual motions and collisions can never be verified. Using them as a reference for why macroscopic properties are changing is extremely effective. It describes processes that take place. It predicts processes that will happen in the future if certain changes are made, which makes it a very useful theory in chemistry and physics.